Okay. I'm assuming that everyone can hear me now because for some reason the mic mute button on my headset was stuck. Okay. So welcome to Math 430. A nice late start due to internet mishaps on Monday. Usually the way that this will work is that basically I'm not going to show up 15 minutes early. Normally because that would lead to annoyance when it comes to actually watching these things. Um, if you want to watch the lectures, later, it would be kind of annoying to always have like 15 minutes of dead time. I mean, obviously you could skip it, or I could just add a timestamp for it. But typically, what I'll do instead is I'll show up, like 3 or 4 minutes early. Before we start, and you show up to the channel and wait for the live stream. Or I may just schedule the live streams to occur at that time so you can show up early. Regardless, I'll continue posting links to the lectures when they happen on Monday, Wednesdays, Fridays until next week. I'll stop and then everybody can just show up at the time. So they'll always be happening here. Sometimes it might happen that, for instance, on Monday, there may be some technical issues on one particular day with actually streaming, at the appointed time. And so in that instance, I'll just stream at some other point, or I'll just record it and upload lectures. So that's how it will work. But before I get into any of that, so I'm Terrence. I don't have a camera on me because I didn't want to, cover any point of the screen. But I'm just going to go through. I posted the current syllabus on the syllabus page. So just going through some of this. So here's what the textbook looks like. 4 pillars of geometry. I'll get into, first question you might have when you hear a title like that is, what are the 4 pillars of geometry? So I'll talk about that here in a second. But we're going to pretty closely follow the textbook. You will have occasional homework, so roughly maybe one homework assignment every 1.5 to 2 weeks ish, something like that. So the homework assignments will come both from this book and from assignment or from questions that I write. So it's nice to have the book for that reason. For those of you that don't have the book, I will, if I'm using the textbook to assign homework, I'll try to take pictures of the problem sets and questions so that you can have them even if you don't have a physical copy or otherwise a copy of the book. Lecture format, that's what I was talking about before. So basically, this is how it's going to go. So you see there's chat. So that's, you can ask questions whenever you want in the chat, and I'll try to get to it. I'll be, taking periodic breaks to answer questions I get in the chat. As far as showing up to lecture, like I said, typically I'll be here just a few minutes early so that there's not a huge amount of dead space. In the videos when you're watching them, in the event that something like that happens, I can always just edit out the first, 10 minutes of the video or something. But anyway, so that's how it's going to go as far as that. Mostly you'll just show up to the channel and join the live stream whenever it happens. It'll be starting, 3 or 4 minutes before noon. So this is how it's going to be. YouTube normally, so in the spring, typically lecture videos would be uploaded automatically, 3-ish hours after stream ended, but since the summer, it's been a lot. It's been a lot more iffy on that. So a lot of my lectures for my summer courses weren't getting uploaded until 20 plus hours after they've been recorded. So almost a full day delay. So just beware of that if if you plan on watching a couple of lectures recorded, then they may be delayed. I don't know. I'll see how long it takes them after the first couple of lectures. let's see, what else I want to say. Oh yeah, so main point that I pointed out in the syllabus and in announcements before is there's not going to be any time-sensitive synchronous assignments. So you're never going to have to like show up and sit, in a Zoom room or sit in stream or whatever for some kind of assignment. It's not going to be timed like that. The only assignments that you're going to have, you're always going to have at least 24 hours to do. So the way that exams will work will be similar to homework. It's just for homework where you might have like 5 or 6 days to do it. For an exam, you'll have like 1 to 2 days. So the way that it'll work is I will post the exam to Elms and then so I'll post that and make an announcement that I posted it, and then you will have 1 to 2 days to do it. Let's see. As I said, yeah, homework is roughly like I say roughly once per week here. It's probably going to be more like once per 1.5 weeks. I haven't set the exam dates yet, so I will put an exam schedule up on the syllabus page on Elms when I've decided exactly where I'm gonna stick those. And then the office hours, I haven't determined a time yet, but sometime on Monday, Wednesday, Friday, I will have every week I will have like roughly an hour-ish of office hours just for this class. So they will also be a YouTube live stream, and I will basically be sitting here waiting for you to ask questions, and I'll answer questions in the chat, and then if they require more than just a couple of lines of typing in the chat, then I will unmute myself and actually put pen to paper. So those are the big things. Also about YouTube, so the channel itself will be more cleaned up for the course here in the next couple days. So I'm going to add all of the 430 lectures to a playlist titled Math 430. So I'm going to have everything organized as far as that goes. So if you wanted to, just look at a group of the 430 lectures, then you could go to that playlist, and I'll add them to the playlist pretty much immediately after I do it. So they should the entire bulk of all the 430 lectures should always be in the playlist for Math 430. I think that's it. I may occasionally add timestamps to videos if I want to isolate things, from a particular lecture that I want you to notice. I believe that's it. I think that hits all of the important stuff. If you have more questions that you can think of, you can ask me in the chat, and I'll answer them. So, getting back to this question. Textbook is called Four Pillars of Geometry, so naturally you have a question about what the four pillars of geometry are. So, first, you might ask the question, like, what is geometry? And immediately you probably have some kind of answer, like, geometry is the study of geometric quantities, right? And so what's a geometric quantity? I mean, geometry, like literally, like geo is like earth and metry is like measure. So, if you're thinking like practically geometry is like earth measure, it's not totally off, right? Because the things that, if you say that it's a study of geometric quantities, what are geometric quantities? So they're the objects that, you studied the first time you studied geometry seriously. So points, right? There's points. What is a point? Well, maybe you say it is a zero-dimensional geometric object, right? But it might be kind of hard to come up with a definition that, is not circular in some way for what a point is. And so to avoid some of this, needless or needlessly complicated wordplay, ancient geometers would just say that there are some common notions. There's some basically there's some ideas of geometric objects that didn't need to be very strictly defined. It's just that you would understand what these things are. So we'll talk about that uh, a little bit more later. So we have points, and then we have lines, and of course this line is an ideal thing, meaning that I've drawn it like this, and clearly it has finite length on the paper, but the idea is that even if I don't always draw these arrows, the idea is when I say that I have a line here and I've labeled my line, say L, that this line is continued indefinitely in both directions, and we'll talk about exactly what we mean by that a little bit later too. So I have points and lines, and then of course, let's say I have lines, I have pieces of lines. That is the piece of a line that is, say, between 2 points that are on the line. So on this line, I pick point A and another point B, and then I can talk about, this line segment AB here. Okay. So looking at this thing, now I have a piece of this line, and once I have a piece of line, I can think of various shapes and stuff that are made up of these line segments. So all of the polygons. So simplest type of polygon would be just a triangle. Oh, that looks pretty bad. Right, something like this. So it's made up of 3 line segments. And from this arises, the study of all of the geometric things that you're interested in. Of course, the second that you have something like this, now you've taken these 2 line segments and you have joined them in some way. And so there are angles here, right? So I have points, I have lines, I have pieces of lines. I can form objects that are made up of these pieces of lines. Once I do that, once I stick 2 of these line segments together, the way that I describe how they're stuck together is in terms of an angle. So, this is where my geometric objects arise. So then you might say, okay, geometry is the study of these geometric objects I've defined like this. Of course, what are the objects I'm talking about? So points, lines, figures made from pieces of lines, angles. Of course, the second you have line segment, you can talk about the length of the line segment. So I could associate lengths to all of these sides. So angle measurements, lengths, that's where the metry comes in geometry. This is concerned with measure or length. So all of the geometric quantities that I'm interested in, notions of length, distance, and angle measurements, arise in this way. Now you might say, why am I interested in those things? And the answer might be, oh, those things are inherently interesting, right? Of course, out of a practical concern, these things are interesting. If you're thinking about literally measuring something physically, or if you're thinking of trying to solve a question of how far off the coast is this boat that I see near the horizon, right? So practical matters like that can be answered with this basic geometry stuff, but maybe you're just interested in it, for its own sake. But this is one way you could define the study of geometry. It's the study of these geometric objects like this. Okay, so before I get into, whether this is a correct characterization of geometry, so what are the 4 pillars of geometry according to this textbook? So I will spoil the fun. Rather than, feeding you one at a time and not telling you where this is headed, I will tell you all of them up front. So first one is Euclidean compass and straight edge construction. So this is Euclid's axioms. Really, what we mean here are compass and straight edge constructions. Okay. So, Euclid's axioms, where did these come from? So, Euclid was a geometer from Alexandria that wrote a textbook called The Elements. So, this was written about 2,300 years ago. So, this is roughly 2,300 years ago. And The Elements was a textbook in the modern sense. In fact, I mean, pretty much every math textbook you've ever seen is modeled on the Elements, because this Euclid figured out this way of exposition that is basically the optimal way of explaining anything in math, which is you start with a list of axioms or common notions or postulates or assumptions that you don't prove. So you just assume this list of things and you say, these are my assumptions. And then from that proceed a bunch of lemmas, propositions, theorems that are things you prove from those axioms or those postulates or assumptions. Okay, and so this is what Euclid did in the Elements. I'm going to be referring to this actually quite a bit, and I may even have you all refer to pieces of it. All this is publicly available, so whenever I do that, I will give you the website. But this is actually a pretty good reference for the first part of this of this class, because we're going to be following a lot of what Euclid covers in the Elements here. So it's this axiomatic treatment which involves the idea of studying the things that can be constructed using compass and straight edge. So we'll get into what we mean by this. These are idealized things here. So the straight edge is not a ruler. It is literally just a thing that allows you to extend lines. Okay, so it's a straight edge, but it doesn't have a mark or any markings on it. You can't use it to measure things. If you need to measure things, that's what the compass is for. So compass, you might remember, I actually don't have one. The one I ordered from Amazon is still not here. So if it's not here by Friday, I'll have to go to like Staples or something to buy a compass just for this purpose. So if I'm thinking about a compass, right? So imagine that these two pins held together are a compass. Okay, I don't think that takes too much imagination. So the idea is that if I'm viewing the compass as this thing that allows me to, fix some distance here and then trace out a circle, what is it that I'm actually doing there? I'm marking off all of the points that are equidistant to some other point called the center of the circle. And so that opening of the compass itself is me specifying some length. So the only measuring I'm allowed to do is measuring done with compass. There's no ruler markings here. And so things that can be constructed with compass and straight edge, these questions are not readily answerable using just strictly basic geometry. And we'll get into that almost immediately. So you run into this problem of what things can be constructed with compass and straight edge. So it turns out that if we're very careful about how we treat Euclid's axioms, potentially adding in some more axioms that maybe Euclid didn't include because he thought they were too obvious. These were hidden assumptions he had that he didn't even list out because it was considered too obvious by ancient mathematicians because they'd never known another system. So we are going to see exactly how we can proceed using Euclid's axioms and compass and straight edge constructions to basically get the plane geometry that you're used to coming from later, right? So the idea is that all of this was done without reference to anything like coordinates, right? So this is our old school geometry of the plane. Of course, the plane many times called the Euclidean plane. Okay, and so when you see those old school geometric diagrams, you are never going to see coordinates, right? So you're never going to see someone like marking off some amount of distance on axes here and then plotting points, right? You're never going to see this kind of thing where you have coordinates like, oh, this is 3, 1, and this is what is this, 2, 3, okay, and so on. You're never going to see this kind of thing in those old geometric diagrams. And the reason why you're not going to see this kind of thing is that, one, most of the diagrams that were taking place were these idealized things, so you didn't even have a specified length of whatever here. But secondly, this notion of describing geometric objects sitting in some plane that had these coordinates like this was something that came later out of algebra. So wasn't something that was done then. Okay. Now, the reason why I bring this up is that proceeding just using compass and straight edge constructions, once you pass the very basic stuff, some of the constructions and some of the diagrams involved here become extremely, extremely tedious and very, very horrible to actually do. No, you don't. You don't need a compass for construction. As long as you, I should say, as long as you are able to take in, what you're allowed to do with a compass, you don't actually need one. So as long as you're, able to internalize what it is that you're doing when you use a compass, you don't need one. You can, just using your fingers and reminding yourself what's going on is enough. It is fun though to have like some cheap compass for doing these things by hand. It's definitely fun. And so for constructing these things by hand, if you wanted really, really nice pictures, you could definitely do that. You could definitely buy a compass. I don't know. You could probably get one for really cheap. I know the cheap ones can be a little crappy and kind of very annoying to use, but it can be fun to do that. But no, you're not going to. You don't need one. Okay, so the reason I bring up coordinates like this is a lot of these computations or a lot of these things that we want to show using compass and straight edge construction are just too annoying to do it this way. And so what we ultimately want to do instead is try to use the fact that we're living in the 21st century, so we have access to, you all have already seen enough algebra that the Greeks didn't have access to, that allows you to make some of these arguments extremely easy. Okay, so some of these arguments are really, really easy to make if you use the algebra at your disposal. So that is the second of the 4 pillars. So the second pillar is linear algebra and just algebra in general. Okay. All right, so linear algebra is going to let us replace a huge number of these terrible diagrams with very, very simple arguments instead. So this allows us to make some very tedious arguments completely trivial, or mostly trivial. At the bare minimum, we get something to deal with that's much, much easier than if we were to try to do this in the Euclidean way. Okay. So when you talk about linear algebra, right, you're talking about using everything you have at your disposal from the Cartesian plane here, using coordinates, using vectors and matrices in order to describe what it is that's going on here. This is going to make so many things so much nicer to deal with. So this is important. This is going to be the second chunk of material. So that is going to lead to the following third pillar, which is projective geometry. Okay. So projective geometry is something that many of you might not have heard of before. Your main experience with this most likely is going to come from any kind of art studying that you've done, because this can arise in multiple places. So one of the first theorems in projective geometry is this called Pappus's hexagon theorem, which we'll talk about. So there were early theorems in projective geometry from thousands of years ago, but the kind of the most likely place that you've encountered this before is perspective in paintings, drawings. And we'll see some examples of where this arises. So for instance, well, here's an idea, right? So so here is horizon line, okay? If I want to draw if I want to make use of perspective, so I'm an observer standing somewhere off camera here, I'm looking toward the horizon, and looking toward the horizon, I'm standing like right in the middle of some railroad tracks, okay? Now, if you ask me to draw railroad tracks, that I'm looking at, you may say, well, I know railroad tracks are parallel, and so when I draw them, obviously I draw them, okay, this is terrible. But obviously I draw them like this, right? But of course that wouldn't really make sense. If I just took this and moved it here, that doesn't look like this is approaching the horizon at all, right? So what do I do to make some somewhat realistic looking drawing of two train tracks that are going off, across the horizon? Well, I would draw them like this. Something like this, right? And yeah, maybe that's not the absolute greatest drawing ever. The idea is that I've drawn two lines that look like this, and this is supposed to be some kind of either railroad or some kind of edges of a path. These edges are parallel, right? Now, this might not make a whole lot of sense at first, because you're like, wait, I want to try to come up with the notion of lines being parallel here. I want to try to display, two lines being parallel, or two, edges being parallel, whatever, here. But instead of making them actually parallel, right? Maybe if you wanted to make them actually parallel, they would do something like this. Instead of making them actually parallel, I have them actually meeting at this point, right? They are emanating from this same point, right? So the idea here is, intuitively what I'm doing might not make a whole lot of sense, right? Here's two parallel lines and these are not. But in terms of the perspective, this looks more like two parallel lines approaching a horizon, whereas this doesn't look like anything, right? This gives me no perspective. This looks completely completely flat. This doesn't look like anything, okay? But this gives me the illusion that there's some horizon line there once I've explained to you what this is. So this is where projective geometry comes into play. The way to think about projective geometry is it's a much cruder geometry. The way of thinking about projective geometry is that only collinearity matters. Okay. So what's a way of thinking about, or what's a way of interpreting this? So only collinearity mattering means that in projective geometry, the things that we can talk about, let's go back, let me bring back my sheet here. So in typical Euclidean geometry, the things I could talk about are points, okay, I can always talk about points. I can talk about line segments. The second I can talk about line segments, I can talk about the length, right, of line segments, so distance between 2 points. I can talk about angles. Well, it turns out in projective geometry, those things don't really make that much sense. So in projective geometry, notions of distance don't necessarily make that much sense. Notions of angles don't really make that much sense. And so what actually matters in projective geometry is collinearity of points, meaning the relationships between points. If you have a handful of points in projective geometry, what matters is not, say, something like the distance between those points. That's actually not something that you can really talk about in a coherent way in projective geometry. All you can talk about is whether or not those points lie on the same line. Okay. So projective geometry is a cruder thing, but it turns out that essentially all of geometry sits inside of projective geometry. So in some way you have to go to this cruder form of geometry to kind of understand a lot of the stuff that's happening under the hood. Okay. And so this is also going to explain where the algebra comes in. Okay, or it's going to give insight into why the algebra helps with geometry. Okay. All right, and so the last pillar is the most important thing for getting a good grasp of how to think about geometry that has been done up till now. This is the most important thing, and this is Klein's Erlangen program, or transformation groups. Transformation groups, what we mean here are groups of isometries. Groups of isometries. Okay, so I'm going to isolate 2 words here. So group, that is the mathematical notion of group coming from abstract algebra. So if you haven't seen a treatment of groups before, don't worry, we'll go over what you need to know for this. So I have a group G in the mathematical sense. So this is a set G equipped with a binary operation we'll call star that satisfies a few properties. So it's associative, inverses exist, which means if you have any element in G, you can invert it. What does inverting it mean? Before I talk about what inverting it means, I have to say that identity elements exist. So there is an object 1 in your group G. And then inverting an object in your group means that there exists some element you can star it with to equal 1. Okay, so a group G is a set that has a binary operation that satisfies these 3 group axioms. Okay, so it turns out that when we're discussing these transformation groups, these groups of transformations or groups of isometries, as long as we're talking about isometries here, these are always going to form a group that we can talk about. And so what are the isometries? So isometry, I'm going to write it again here. Well, iso means same, and metry means measure, or distance or length. Okay, so isometry literally means same measure. What is an isometry? So Euclid called these rigid motions of the plane. The idea is that I have these geometric quantities that I'm interested in inherently, right? So points, and then distances between points, so length of line segment connecting 2 points, angles, right? I'm interested in all these things. Okay, and because I am interested in these things, I am also interested in transformations that preserve those things in some way. So, for instance, if I take my plane and I apply a transformation to it. So let's say I take this picture and I rotate it. There, I rotated it in some direction about some point, and I look at these same objects, right? Now, they are not the same objects I started with, because here's those objects, and now the objects I have are, they're in a different location, right? So they're not the same, okay, but they are the same in terms of some idea of congruence, right? Meaning that this length between A and B wasn't changed by what I just did. This triangle that I have drawn here, those angles weren't altered by what I did. In fact, all those were exactly the same. Okay, so rotation works. Okay, what else can I do? I can mirror these. I could flip them. Now, you can't see that well through the paper, but in reflecting them about some line, again, what have I done? I haven't altered these measurements, so I could trace them if I wanted to. I'm not going to do that, but these angles here, these angles haven't changed. These lengths haven't changed through my reflection. I could slide this around, right? I could translate this image, and nothing has changed here, right? Those lengths are still the same, and those angles are still the same. I could do a combination of those things. So I could rotate and then translate and then reflect, and again, none of those quantities that I'm interested in have changed. So for that reason, we're interested in isometries inherently because they fix these quantities that we're already interested in and want to study. Okay, so that on its own should tell us that we should be interested in isometries. This last thing, so Euclid's axioms, composite straight edge constructions, this was roughly 2,300 years ago. The algebra that is going to make our life easier was developed over hundreds of years, leading all the way up till, we'll say like the 1500s, 1600s is where this kind of, what we're going to use, well, maybe a little bit more than that for some of the algebra we're going to use. Projective geometry, again, there were some ancient theorems about projective geometry that weren't quite considered. So basically, they were theorems stated in normal geometry that were actually theorems about projective geometry, but it wasn't necessarily noted the relationship between that and what we're going to talk about here. But you know, all this perspective and paintings and drawing stuff, this arose in like maybe by the 1400s, 1500s, and then this Erlangen program is late 1800s. So this is like 1870s, 1880s. So this is you know, compared to all the rest of this stuff, this is brand new. Okay, this is very new in terms of what the rest of everything that's studied. And so this approach is actually it is the converse or the opposite direction of what I originally said here. So here, isometries are important because they fix or leave invariant these quantities that we're interested in, right, already. But this says the opposite. This says that actually what are important are the isometries. So it's the isometries themselves, these transformations, that are important. And the reason why these objects are important is because they are the objects that are fixed by the isometries. So it's kind of a backwards way of looking at things. It's originally Euclid used the fact that he was interested in this to figure out what the isometries were, and the isometries were only something that was interesting because of that they left these invariant. They fixed these objects. So Klein reversed that, saying that actually, you know, it's the isometries themselves that are inherently interesting, and what looking at the objects they fix, this backwards direction is something that allows you to talk about geometry in a much, much better way. And so how is this going to work? The idea, so maybe I'll continue here. So idea behind Erlangen program. So the idea is one, pick your isometry group. And two, this determines your geometry. So this statement is maybe a little fishy here, right? So up until now, I began with the question, what is geometry? My first thing that I wrote down after that, of course, was Euclid's axiom, compass and straight edge constructions. And so inherently what my secondary answer to that was geometry is Euclidean geometry. Okay. But as I believe the official title of this course is Euclidean and non-Euclidean geometry, the beans have already been spoiled in terms of what is true. That is that there exist non-Euclidean geometries. Okay, but the question is, how do I get at those? Okay, so this is a very convenient way to do that. We're going to talk about many different characterizations of non-Euclidean geometries, and we're going to give plenty of examples of non-Euclidean geometries. So for instance, projective geometry in pillar number 3 is already an example of a non-Euclidean geometry. And the reason, one thing that we can talk about, or one thing to note how this behaves is exactly this statement that only collinearity matters. This gives rise to something that's non-Euclidean. But forgetting about that for a second, in this way, what I mean by determines your geometry is you pick your group that you're going to call your isometries, that are going to be the group of isometries for the geometry you're studying. This determines your geometry, meaning that changing the group here changes the geometry that results. So if you want to study Euclidean geometry in this way, the isometry group you pick would be the group of Euclidean isometries. Okay, and we're going to talk about that specifically. But if you alter that isometry group, if you pick a different group of transformations here as your isometry group, this can lead to different types of geometry. So hyperbolic geometry is one of them. Okay, so this is the clearest way of arriving at non-Euclidean geometry. Although we are going to see examples of non-Euclidean geometry throughout. Okay. But this is not a trivial realization, so non-Euclidean geometry was not known to exist really until the 1800s. So not known to exist until the 1800s. Okay. So Janus Bolyai and Nikolai Lobachevsky independently came up with the first full formulation of a non-Euclidean geometry. Okay, in the 1800s. 1830s for Bolyai, I think, maybe 1840s for Lobachevsky. I can't remember exactly off the top of my head. Why is this important? First of all, what is non-Euclidean geometry? So just a quick and dirty definition of something that's non-Euclidean is the parallel postulate is false. Okay. We are going to discuss what the parallel postulate is in great detail. Okay, we will discuss this at length and why it is important. The quick question, or a quick way of answering what the parallel postulate is. Parallel postulate is, there's a form of it that I'll state that's the easiest to state. That's called Playfair's axiom. It's equivalent to Euclid's original parallel postulate, which says that if you have a line and a point not on the line, then how many lines can you draw through this point that are parallel to this line L? Well, one. There is a unique line that can be drawn through point not on line that is parallel to this original line. Okay, that is equivalent to the original parallel postulate. It turns out that in non-Euclidean geometry, this is not true. So we are going to see cases where there are no parallel lines. We're going to see cases where there are infinitely many. Okay. And so if that's causing you to scratch your head, don't worry. We will see exactly what it is that's going on here. The idea is, what makes this thing that I've drawn here a line, right? And then what are the lines in other geometry? Okay, so we will talk about those things. That's why this course is going to be a lot of fun, because we're going to spend a lot of time talking about exactly those things. So anyway, why might you be interested in non-Euclidean geometry? Well, I mean, you're mathematicians. I shouldn't have to give you any kind of motivation for being interested in anything coming from anywhere, any outside concerns. The idea is, there's things that are interesting just because, right? They're interesting for their own sake. But if you absolutely, demand that I give you some reason why you might be interested in non-Euclidean geometry, not for its own sake and not for the fun that results in, studying it, well, then you probably already know that Euclidean geometry was originally meant to be a model for the geometry of, locally, like the surface of the Earth. And then, later, thinking of like the Euclidean geometry of space, again, to be a model for space. But of course, Euclidean geometry is synonymous with the idea that space is flat, or the space that you're dealing with, or whether that's plane or Euclidean 3 space, is flat, meaning no curvature in some way. But we know that that's not the case for, say, the universe, right? So the universe is not flat. There's curvature in places, right? There's places with curvature that is non-zero. And so necessarily the geometry of the universe is non-Euclidean, right? And in fact, before anything like relativity could be formulated, what had to be understood was non-Euclidean geometry, because the geometry of a space that is, non-Euclidean, or a space that is curved, is necessarily non-Euclidean. And so geometry must be studied in this way to even, there's no way to discuss, how can you discuss things like curvature if you're assuming that the curvature is zero everywhere, right? And we're gonna, I've done some hand waving there, but we're going to talk about all of those things. But, the short and narrow of it is that non-Euclidean geometry turns out the geometry of the universe. So in a way, non-Euclidean geometry is the realistic geometry, whereas Euclidean geometry is the, unrealistic, idealized geometry that is, purely like an invention of the mind, right? So anyway, that's mostly the idea. So those are the 4 pillars. And if you look at if you look at the contents of the textbook, the first 2 chapters are for the first pillar, and it proceeds like that from here on out. So the first 2 are Euclid's axioms and compass and straightedge construction. Chapters 3 and 4 are algebra, linear algebra. 5 and 6 are projective geometry. 7 and 8 are transformation groups, the Klein-Zerlangen program. Ultimately get to non-Euclidean geometry. So that is the goal. That is where we're headed, and we should get through this entire book. So I will stop now since I'm out of time, and we'll start here on Friday. So anyway, welcome to the course again, and same format on Friday. I'll join like 5 minutes before lecture. If you have any questions before that, let me know. You can email me, or don't be too shy to ask in chat. But anyway, I have to teach 461 after this, so I got to go so I can, typically I'll be able to hang a little bit after lecture to answer some questions, but since today is also their first day of lecture due to Monday's internet problems, I'm going to go and be there a little bit early for them. So I will see you all next time.